spheres, the uniqueness problem. There's a recording. Also her work on sort of static asymptotically flat systems, geometric inequalities satisfied by horizons, and relating angular momenta horizons and so forth. And finally, her work on quasi-local mass, Bartnik mass. So all these problems are very geometric, mathematical in character, but also, tied closely to physics. So the stuff she'll be talking about today, as you can see, will be about the center mass problem. So I'm really looking forward to this, and I'll let Carla go ahead. Thank you very much, Carla.
Thanks, Harry, and thanks, Ivan, for the introduction and the invitation. And thanks also from my side to everyone who's joining from around the world at various time zones. And welcome. And let me start by saying that I'll be happy to be interrupted by questions through, I understand, the Slack channel. And at any time. And I may ask you to wait for a moment because that's the next thing I'm going to explain, but I'll please make sure that you ask any questions that come up right away when they come up, so I can address them and not go ahead too fast. The plan for my mini course, and I hope this is a good replacement of the Blackboard I would usually be using, will be to start with initial data sets and the notion of extrinsic curvature. Some of you may be familiar with both or either of them, some not. So I'll start very slowly, and I'll try to introduce everything I'm going to talk about later. And then I'm going to introduce the concept of asymptotic flatness of initial data sets. And then I'll talk about energy, linear momentum, and mass of asymptotically flat initial data sets. And I'll do that rather briefly because this is extremely well understood, but I want you to get some feeling for the theorems and notions that exist there that are relevant to physics and to math, and in particular relevant to the last part of the mini course, and that would be the center of mass. And that part is very much tied to the idea of a foliation. And I'll say what that is tomorrow. So if there are no questions right away, I'll start with part one. No? So let me jump right in and say an initial data set is a situation where we are given an M3G, which is supposed to be a Riemannian manifold in 3 dimensions. And my signature for a Riemannian manifold will be plus, plus, plus. Then there will be an object K, which will be a symmetric 0-2 field on M, and symmetric, and I'll talk more about its interpretation in a moment. And then there will be variables mu and j, called meta variables, where mu is the energy density and j is the momentum density. And mu is a scalar field or scalar function on M, and J is a one form. So such data, a manifold M with a Riemannian metric G and a symmetric 0-2 tensor field K and a scalar field mu and a one form J is called an initial data set. And I'll try to explain to you why. And I'll also try to give you more information about what this K is and mu and J are in a second. So let's first draw a sketch. So we have a space-time for ds squared. So my a name for a Lorentzian space-time matrix will be ds squared, and the signature I'll be using will be minus plus plus plus. So this is a Lorentzian space-time, and assume we have some kind of time coordinate or time function here. So t time. Then we can look at level sets of constant time. So say, for example, t equals 0, and this will be what we consider as m. This is why it's called an initial data set. It's initial data for the space-time. Another word people are using is to call this a time slice of the space-time. Okay, and then what are the objects G, K, mu, and J? Well, G is what we call the induced metric. And M here. So if I have X and Y in TPM, so tangent vectors to M at some point T, X and Y, then G at P of X and Y is nothing else as ds squared at P of X and Y. So it's exactly the same information that the Lorentzian metric ds squared, the space-time metric, has about this point and these two vector fields at this point, except that I'm not allowed to plug in the vectors that are not tangential to this hypersurface, to this initial data set, or to this time slice. So this is the formula for the induced metric. So nothing very ingenious going on there. What's important is to remember that G is Riemannian. So of signature plus plus plus, precisely if and only if, so this is a mathematical symbol for if and only if, G P of X, Y, sorry, X, 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 X is bigger than 0 for all non-zero vectors X in TPM and all P in the M. So if the metric is positive definite, by definition, and this is equivalent to saying that the unit normal vector field N to M time-like. So in the signature I'm choosing, this says that ds squared n is less than 0. And by normal vector, I of course mean that the color there, but normal means that ds squared n x is 0 for all x tangent. So I can draw my little normal vector in here. Okay, so that's what a normal is, and it's an easy exercise. And if you're not familiar with this, I recommend to show this as an exercise to see that the induced metric on a hypersurface is positive definite if and only if the normal vector field is time-like. Okay, so then that's what G is. What is mu? The energy density mu. Mu is defined as 1 over c squared times t of n, where t is the energy momentum tensor of the spacetime. Some people also call it the meta tensor of the spacetime, and c is the speed of light. And you may want to set your unit such that the speed of light is 1, and we will likely do so later, but for now, let me keep the speed of light there. And n again is this normal vector to the slice, to the time slice, to the initial data set. And the momentum density J defined as minus t of n, and a slot which is allowed to eat vectors to the hypersurface. And this is where I start saying beware. So I say beware, the sign here sometimes is there and sometimes is not there, depending on the conventions used in a specific textbook or research paper. So this is one of the signs, and we'll see this frequently in this mini course. The signs are conventions, and this is the convention I'm using. And if you use another source or resource, then beware to check which signs they use in their work. Okay. So let me go back and say what we did. If I have a spacetime L4 ds squared here, together with some meta tensor T, describing the meta content of the system, and then I look at this hypersurface arising, say, for example, as t equals 0 in this spacetime, then automatically I inherit from the spacetime metric ds squared, a Riemannian metric, if I choose my slice wisely on the slice. So this, I also automatically have this normal. I'll say something about the normal again in a second. I have this energy density and the momentum density. I didn't say what K is yet. Maybe you noted. But before I'm going on to say something about K, let me make a remark about the normal. So N always exists locally, but not necessarily globally. You know this from the Möbius strip, for example, that it's not possible for every hypersurface to have a global unit normal vector field. Yeah. Compare the Möbius example. That I presume you're all aware, otherwise I'll be happy to explain if someone has an explicit question about it. But here, and in most of what I've seen of general relativity, when people are not specifically talking about this issue as a matter of interest, we assume that a unit normal vector field exists globally. VF is vector field exists globally. And this follows from some orientability assumptions and time orientability assumptions that I'm not going to make explicit because they're not in the central interest of this mini course. Okay, and also we use the convention that N be future pointing. Okay. So this is exactly what I already suggested in my sketch. And the green vector N is a future pointing unit normal to this initial data set. Okay. So then what is really this K that I was talking about? So the name for this K is extrinsic curvature tensor, or in the more mathy literature, it's called the second fundamental form. And I'll define it in a second, but let me start by saying two things about these names. So why is it a second fundamental form and not a first fundamental form? Well, because historically, what I call the induced metric G here is what people used to call the first fundamental form. Okay, so some people also call it here the first fundamental form. That's pretty outdated by now. Not outdated at all to call this object K that I'll define in a second, the second fundamental form. So if you're ever wondering why there's only a second or the first fundamental form, it's because the name for the first fundamental form changed to induced metric. So now what does it mean to be an extrinsic curvature tensor? I presume all of you have seen the Riemann curvature tensor of a space-time or a semi-Riemannian manifold or quasi or pseudo-Riemannian manifold, whatever you want to call it. And the Riemannian curvature tensor talks about intrinsic curvature, curvature that you find when you draw a triangle on an infinitesimal level and compare the angle sum to the 180 degrees you will find in the plane. That's intrinsic curvature. Curvature you can't smoothen out by changing the position of something in something larger, but it's an intrinsic quantity. The curvature we're talking about here is extrinsic curvature. So it's only meaningful if there is an ambient space or space-time in which we're talking about this extrinsic curvature. And then the extrinsic curvature is information about the curvature as perceived from the outside. So for example, a very naive example is if we have a cylinder in our Euclidean space, it definitely looks curved. But intrinsically, from an interior perspective, if I'm a two-dimensional bug is an analogy we like to use in math. If I have a two-dimensional bug living on the cylinder that doesn't see the third dimension going away from the cylinder, then this bug will not know that the cylinder is curved because it doesn't locally, it doesn't see a difference between a piece of the cylinder and a piece of the paper when I rolled it out. In other words, in more mathy terms, rolling the cylinder off is an isometry which doesn't change metric information and thus not intrinsic curvature information. On the other hand, to us three-dimensional people, from the outside, the cylinder, of course, does look curved, and this curvature is actually there. It's just not intrinsic, but extrinsic, and depends on our perspective from 3D Euclidean space onto the cylinder. And what is curved about is that the normal vector that my finger now indicates, or let me take a pen, my normal vector changes in a non-trivial fashion when I move around the cylinder. While in contrast, if I have a flat sheet of paper, which is both intrinsically and extrinsically flat in Euclidean space, then if I look at the normal just wanders around in a parallel fashion if I wander around with the tip on my hypersurface paper. On the other hand, if I roll this to a cylinder and I look again at the normal, then it doesn't parallelly translate. It actually rotates around the cylinder. So that's this extrinsic curvature, I mean, just in an intuitive way. And hence the definition of my second fundamental form tensor K, or extrinsic curvature tensor K, is to take two vectors tangent to my hypersurface M, which go into R. Second, there's a question in the chat. Yes, please. Ask your question. Oh, I'm not sure I can unmute you.
Yes, we could do that. Maybe I'll ask Ivan to do that just to make sure he does it. Or, you know, we asked that the questions be given in the Slack, and then I can read them out to Carla. So maybe that's easier.
That's easier.
If you could just type it in the Slack. Thanks. That might take a second, but okay. Next time if anyone has a question.
So in that second, I'm going to try to write down the definition of the second fundamental form. So if I take two vectors, then I map them to G, nabla X, N, Y, where this nabla here is the relativity connection of the space-time metric. Okay, so this tells me the rate of change of the normal vector in direction of a vector X. So I can move according to the flow of the vector field X, and I look at how my normal vector changes, and then I project it down again onto the tangent plane to the cylinder by pairing it with Y. Then this tells me what the extrinsic curvature is. The question there, you know?
No, I don't actually see it. Maybe you're just typing that in, or maybe it just takes a second to figure out how to get that thing to work.
Okay, I'll just wait for you to interrupt me then, Harry.
Sorry about that. Yes, I may interrupt you.
All right. So the formula I just wrote down, this here, is the formula for the extrinsic curvature interpreted as the rate of change of the normal vector in some tangential directions. Okay, and here are a few facts that I won't prove nor explain in detail, and then I ask you if you want to have an exercise to verify these as an exercise, and you will find them basically in every textbook on submanifolds or hypersurfaces, or a lot of textbooks on GR. And one of the facts is that K is a symmetric 0-2 tensor field on M and actually smooth. Another fact is best captured by a formula, namely K of X and Y can be computed also like this for X, Y, vector fields on the manifold. So that means instead of looking at the rate of change of the normal vector in tangential directions, I can look at the rate of change of tangential directions, again, within the space-time. So with respect to the Levi-Civita connection, or the Christoffel symbols, if you for the space-time, for the ambient space-time, and then project onto the normal vector. This is a fact. And then there's another fact which has a name, and it's called the Gauss formula. And it says that if I want to compute the Levi-Civita derivative or connection derivative of a tangential vector field y to my hypersurface in the direction of a tangential vector field x to my hypersurface, then what happens is that I can do this completely within the hypersurface. So with respect to the Levi-Civita connection of the Riemannian metric on the hypersurface, plus second fundamental form of x and y in the direction of the normal. So this, let me write it down, is modular 2 is the Levi-Civita connection on MG. Any questions?
Yeah, I still hadn't seen it, Carla, on the, so maybe it just for those who are interested, there's in the Slack channel, there's one called mini courses. So if you just put your question in there, then I'll read it out when Carla asks for questions, and she's asked for them throughout. I hadn't seen one yet.
Okay. Oh, there's something. Oh, maybe if there's a problem with Slack, maybe they can type it into the chat also, Harry?
Yes, that's fair enough, actually. It does seem to be there. The last message was sent by Ivan just a little while ago, maybe an hour and a half ago. So it looks like it's working. Maybe I'll just type something in there now. But if you do have a problem, the person who did ask the question, and Pawan, that is, you can type it in the Zoom chat if you're really having a problem with it. It's okay.
So while you're typing, let me make another sketch. So here, a different way to draw our hypersurface M in our spacetime L. And I look at some point P inside there. And then I look at the tangent vector X to M starting at P, and another tangent vector Y in to M starting at P. And I'm looking at the normal in orthogonal with respect to the spacetime metric to M at P. And then what I get is this what this Gauss formula tells me is that I have this vector blah x y, which is a space-time vector to begin with, taken the derivative of this vector field x, a y in direction of this vector field x, understood and somehow extended to a neighborhood of this manifold M, so that I can take this derivative And then what I'm doing with this brown vector field nabla xy, which is now a space-time vector or vector field at this point P, is I'm decomposing it into its part parallel to n and the part parallel to the manifold. So this part is parallel to n, and this part down here is tangent to n. And then what the Gauss formula tells me is that this tangent part is nabla xy. So pretend there is no ambient space-time and just look at this Riemannian manifold and compute the derivative of y in direction x there. And this part here is k x y in n direction. So k x y tells me how much in n direction I have to go to meet this brown vector. Okay. So this is a sketch of the Gauss formula, what's going on. And here is the next remark. The definition of k is not uniform in the literature, and some textbooks have a minus here. But I'll remove it immediately because I won't have it. And this has consequences for this formula, of course, when they'll have a plus then. And also they will have then a different sign here, potentially, depending on which conventions they use. So those are the places where you need to watch for signs as well. Okay, so much for the extrinsic curvature tensor for the second fundamental form. So now I hope I convinced you that there are valuable definitions of all the names or symbols I put in the definition of an initial data set. So let me review. An initial data set, and now as a mathematician, I'll be happy to take this as some abstract object. I hope I convinced you it occurs in space-times, and I will convince you more of that in a moment as well. So an initial data set to me is a Riemannian three-dimensional manifold MG with an object K that is a symmetric 0-2 tensor field on the manifold that I'll interpret. If there is an ambient space-time, I'll interpret it as the second fundamental form or extrinsic curvature tensor of the initial data set in the space-time. And there's a scalar field mu and the one form field J on M that are matter variables coming from the space-time matter variable energy momentum tensor T, or just given to me by some mathematician or physicist. Okay, this is what an initial data set will be. So let's look at some examples. And let me introduce the abbreviation IDS for initial data set, which you'll also find a lot in the literature. So then the most prominent example, and probably the most boring one as well, is this one. Let me write it down first. So this is Euclidean space in 3 dimensions. Delta is my symbol for the Euclidean metric. Euclidean space. This K tensor that we talked about just a moment ago is 0, and also the matter variables are 0. And this is, in fact, the T equals 0 set of Minkowski spacetime for the canonical time T. So this is this plane in Minkowski spacetime, and this is the time direction. And we call it the canonical initial data set of the Minkowski spacetime. Some of you, and probably most of you who studied special relativism and think of notions I just gave you, K and mu and J and G also, might understand the following. If I take Minkowski spacetime, so I have my space here and my time here in these Minkowski coordinates, and then I boost my G equals 0 set to a boosted time, then again, this boosted initial data set is going to be Euclidean space as a Riemannian manifold, having K equals 0, no extrinsic curvature, flat also exterior, from an exterior perspective, and also vacuum. So again, mu and j will also be 0. So this is an indication that we are in vacuum. Okay, so also boosted planes in Minkowski take this form. Another example that you may be familiar with is if I take Euclidean space outside some ball of radius 2m for some parameter m, which is 0 or positive, or let's have it actually strictly positive for this example, and then the metric 1 over 1 minus 2m over r dr squared plus r squared d omega squared in spherical polars, k equals 0, mu equals 0, j equals 0, where again this tells us that we're probably in vacuum. This would be the canonical t equals 0 initial data set of the Schwarzschild spacetime. And this one, or the Schwarzschild spacetime in itself, would be very important for also for today and for tomorrow. So if you have any questions about this or about my usage of variables or so on, please feel free to ask them already now. And I'll continue because I have no idea about the time lag.
Carla, actually, I did have a question. Maybe this will just get the questions going, but I was curious as well. Is there, I suppose you have two initial data sets, like you give me G and K. Is there a way I can tell they're the same? Is there some, like what's the equivalence between them? Because I guess there's some redundancy in the description.
Not any naive a priori one I would be aware of. Of course, for the Riemannian metric part, I could ask about isometry. If I wanted two initial data sets to be the same, then definitely I would want their Riemannian metric parts to be the same, and then mu and j to be the same under the isometry and the push forward or something. And of course I could ask that also k pushes forward to the same thing, but that seems a little bit too restrictive to me at first thought. So I will mention later that for any initial data set, I can, and given a meta model and say vacuum for now, there is a theorem by Chappé-Bruhat and Gewurz that tells you that there's a unique globally hyperbolic development of that initial data set, which is somehow the maximal spacetime generated by these initial data under the Einstein equations. I'll mention that briefly later. And then I would consider them the same initial data set if the spacetimes they generate are the same, and then they arise as the level set of similar time functions or the same time function in those spacetimes, say.
I see. Okay. No, thank you. That's good, actually.
Yeah. Okay. And then somehow a more abstract example of an initial data set would be that any set of the form p equals constant in any suitably orientable spacetime for any suitable time function t is an initial data set. Is an initial data set in the following sense: if I say m is t equals constant, and I use g as the induced metric, and k as the second fundamental form, is my abbreviation for second fundamental form, and mu and j as above, then this t equals constant set is an initial data set according to the definition I just showed you. Okay, but I want to show you one class of examples that will also be relevant tomorrow when we study the center of mass, and this may be more instructive. So it may be more interesting, rather concrete example that might also give you a feeling for what's going on in these initial data sets. And for this, we consider the Schwarzschild spacetime. So the spacetime metric looks like -1 minus 2n over r dt squared plus 1 over 1 minus 2n over r the r squared plus r squared the omega squared. And the manifold is r plus the exterior of a ball of radius 2m. And here m is positive, but in the computations, it's also okay to allow n equals 0. It's just not usual to call this Schwarzschild, and then it would just be Euclidean space and Minkowski spacetime in spherical polar coordinates. If n equals
actually, Carla, the question did come in now, so sorry to interrupt you. It goes back to the stuff you were talking about before, but I'll mention it and you can answer it. So the question was, the normal vector of a cylinder changes, of course, while the normal vector of a plane does not change, as in the picture you drew. Mm-hmm. And so the question was, is the extrinsic curvature the same for both the plane and a cylinder?
No, the extrinsic curvature is exactly what tells these apart in some sense, in a quantitative sense, right? So for the cylinder, for the plane, the extrinsic curvature would vanish. It's extrinsically flat, so the extrinsic curvature tensor K vanishes for the plane in Euclidean space, or also a plane in Minkowski spacetime. If I roll it to a cylinder, intrinsically, I don't change anything. So the intrinsic curvature, the Riemann tensor of this two-dimensional manifold will still be 0. But extrinsically, there's curvature now because the normal vector changes, and the second fundamental form captures exactly that curvature quantitatively. Okay. So thanks for the question. That's very important to clarify. Okay, so let's get back to our more interesting concrete example. Now there's a follow-up question. What are delta and B JM? So it's not JM, but 2M here, this index 2M, and also this is a 2M. And delta is the Euclidean metric. So delta, let me write it, I'll erase it again in a second. Delta you can either in spherical polars write like this, or you would write it as, or you would write it as dx1 squared plus dx2 squared plus dx3 squared. So that's what delta is. And again, thanks for that question. Okay, so then this is my Schwarzschild spacetime with mass parameter m. Sorry, the chat is, yeah, there's just a thing. The chat is very, that's why I'm always taking a moment. Here is my Schwarzschild spacetime, and then the canonical initial data set I just mentioned. And here is the manifold M, which is t equals 0, and we can now compute it. Actually, the exterior of this ball of radius 2m around the origin. That's the manifold of the initial data set. The metric is just this part here of the spacetime metric, which is arising as the t equals 0 induced metric. Okay. And K, if you compute it, so this is left as an exercise. And T here is 0, and accordingly mu and J vanish here, which is because the Schwarzschild spacetime solves the vacuum Einstein equations. Okay, so this is the canonical initial data set I showed you a second ago. And then here we can look at other initial data sets. So let me draw a sketch. Here's our type function T of Schwarzschild spacetime. Here is T equals 0, our canonical initial data set. And then I can look at graphical data sets. Okay. So what I'm drawing here in green will get the name MT and will be defined as this following set. The pairs T x in R plus M, where T equals T of x. Okay, so now I'm going to call these points in this canonical initial data set x. And then I'm looking at points of the form T x for some T, and one of these points x in the initial data set, such that the time coordinate T is exactly a given function capital T of x. So here, this is given to me T from M to R, it's called the graph function. So this is just like a graph in your calculus, the multivariable calculus course. Now in a space-time setting where what you usually call the y direction or the z direction is called the t direction for obvious reasons, and we can consider graphical initial data sets. Then we can study MT, which is a graph, and we can study the induced metric. UT. And we can study the second fundamental form, AP, and we can study the energy density and the momentum density. UT and AT. And the index capital T indicates that we're always referring to that very same graph function, capital T, that's given to us. And it turns out that it's very easy to see that these are both 0 because the energy momentum tensor of the spacetime here is 0. So all its components, its projections, the matter density, the energy density, and the momentum density, they all vanish. Okay, so we don't have to do any computations. We do, however, have computations to compute the induced second fundamental form and the induced metric on this MT. Okay, I won't show you the full computations. I just want to show you the spirit of the computations, and I'll give you 2 references to read up on this. So references. A paper with Christoph and Merz from 2015 in Annales Henri Poincaré, where we first consider these graphical time slices in the Schwarzschild space-time and do all the computations, but there is a computational error in the second fundamental form, and you find the correct formula for the second fundamental form in my paper with Anna Sakovic, and both of them will play a role again tomorrow when we discuss the center of mass, and this is calculus of variations in PDE. Okay. So if you're interested in reading the full computations, they are in there, and the correct formula again is in the second one for K. But let me explain the spirit. So if we want to write down a formula for the induced metric on this green graphical hypersurface, then we first need to pick coordinates on that green hypersurface. Okay, so pick coordinates.
Carla, I just,
yes.
Sorry to interrupt you. I did have one question, which I think it fits in with what you were asking. Someone asked, how can one intuitively see that the extrinsic curvature of the Schwarzschild space-time is 0, at least in this coordinate system?
This is what I'm leaving as an exercise, you mean?
Yes, I guess someone just asked intuitively why is that, why is it 0?
That's a great question. Thanks, Harry. So I'm having this space-time, and I'll show you, I'll draw up the space-time metric formula again, which is here. Okay, so that's the space-time metric. If you look at that, then you see that none of the coefficients depend on t, and also there are no cross terms with dt and dr and any of the angle variables, which hopefully intuitively convinces you that the spacetime is static. If you haven't heard that notion yet, nothing depends on time, it's static. And the t equals 0 hypersurface is adjusted to that staticity, which is a symmetry in both time translation and time reflection. So if you also change t to minus t in the formula for the Schwarzschild metric, then nothing changes, which means that the spacetime is reflectant invariant under time reflection. Okay? And this hypersurface t equals 0 in the Schwarzschild spacetime is a plane of symmetry under this time reversal reflection or time reflection. Okay, so if I take t to minus t, then all that happens is that this plane stays the same, but its time orientation changes, which is why I'm flipping it around. Okay, but the induced geometry, both intrinsically and extrinsically of this plane, stays the same. And this should tell you, if you're familiar with second fundamental forms or extrinsic curvature, or just intuitively, that there can't be too much extrinsic curvature, because otherwise it couldn't stay the same under time reflection. That makes sense, Harry?
No, that's good. And the follow-up question that you also asked, you're just asking what was the purpose of the graph function? I think you're going to talk about this later.
I'm going to say about, yeah, I'm going to talk about that in a second. So thanks. Maybe I'll answer that right away to make you motivated to understand why we compute them. So the purpose of the graph function is this. If I have any initial data set in the Schwarzschild spacetime, so any space-like hypersurface, any hypersurface with time-like normal vector, or those are all equivalent statements of the same, then I can write it as a graph of a graph function with certain properties. Okay, so any hypersurface in the Schwarzschild spacetime can be written as a graph over the canonical one, or a piece of the canonical one. Okay, so in order to analyze all hypersurfaces, all space-like hypersurfaces, or all initial data sets in the Schwarzschild spacetime, it's equivalent to consider all graphical ones for all graph functions with certain properties.
Okay, thank you, Carla. No, that's really good. So I have to ask a follow-up. Is that just true for Schwarzschild, or is that sort of a general property of these sorts of things?
It's true for every standard static spacetime for sure. It's a little bit more involved, and I don't want to say anything because I'm not in a position to make a good claim about non-static ones, because as soon as you have some rotation going on, then it's not so clear to say which point in the, so first of all, there's no canonical initial data set anymore, so you would have to choose one over which you would write everything else as a graph. And then also because of the rotation or the shift or something like that in the metric, in the spacetime metric, it's not clear which point in the chosen initial data set corresponds to which point in another one. Okay. While in a scenario where we have a standard static metric, so a metric of the form minus some function dt squared plus some time independent metric, because of this time translation symmetry, there is a canonical way to say which point in the blue canonical initial data set is which corresponds to which point above it, because we have this notion of above. Okay, yeah, so, and sorry everyone for, I'm abusing my powers of asking questions. Sorry, Carla, please go ahead. Please. No, that's great. And maybe one last comment. The second fundamental form is a tensor object, so it's completely independent of which coordinates I'm using. Yeah, so the reason why I'm picking coordinates now to the computations is because it's hard to write anything down without coordinates. But the objects are all tensorial in nature that I'm talking about, except of course the time function. Okay, so in order to describe the metric and the second fundamental form on this graphical initial data set, MT, I'll pick coordinates, and what I'll do is I'll call these coordinates yi, and all I'm going to do is I'm going to take the xi, so either r, theta, and phi in polar coordinates or some rectangular version thereof, it doesn't matter, of the spacetime, and restricted to MT. So xi, t, and xi are coordinates and Schwarzschild spacetime. Okay, so I'm picking very canonical coordinates, forget time. Those are the coordinates. So the point with the same spatial Schwarzschild coordinates and just a different time value will the coordinates yi equal to xi. And then the second step is to compute the tangent vectors, the partial yi's tangent to mt. And this is something where a lot of papers make mistakes, so I'm warning you. Those are not the same as the partial xi's. The partial xi's are horizontal. The partial yi's are tangential to the green hypersurface. So I'll draw some. So here's a y1 third and the partial y2 and so on. Okay, so what happens is that what you do is you say, okay, yi is xi restricted to mt, and as a consequence, dyi is going to be dxi restricted to the tangent space of dmt. And then the partial yi's are the dual frame to the dyis. Okay, and duality is depending on which space you look. So partial y, the dual frame to dy. Okay, so you have these canonical tangent vectors to this green graphical hypersurface in this way. And then you can just compute gt, dyi, dyj, and you do some computations that's shown in the paper with Christopher Natz. And what you find is that it's d dxi dxj minus n squared dxi dxj, where n is an abbreviation for 1 minus 2m over r, and this is the lapse of Schwarzschild. And Harry, to your question, if this is any standard static spacetime, then this works with n being the lapse of that spacetime. So let's write this in a different way. So I have GT, the matrix components of GT are the original components of Gij minus n squared Ti Pj, and I'll drop the little x's here for simplicity. Okay. So I can compute the metric, the induced metric on my graphical hypersurface by computing the components of the original Schwarzschild metric and then subtracting the lapse squared and the first partial derivatives of the graph function T. So this is how the graph function changes the induced metric. And then after a somewhat lengthy computation that I'm not going to show, you get that the components of the second fundamental form of this graph can be computed as Bi and j plus Tj and I plus n. Hessian ij of t, where the Hessian is computed with respect to the metric g, minus n squared I j times dn, plug in the gradient of t with respect to g, divided by the square root of 1 minus n squared dt squared with respect to g. And all this is true, provided minus n squared t d squared is positive. That's the condition on the graph function I was mentioning. So what does that mean? I give you a graph function and I ask you, if you look at that graph, is that graph going to be an initial data set? And your answer is going to be yes, if and only if this condition here is satisfied, because that tells me that my hypersurface that I'm considering doesn't tilt too much and become null or time-like. I want it to be space-like. I want it to be a time slice. The normal should be time-like, in other words. So this is a condition ensuring across M that the hypersurface is really an initial data set and not something that is null or time-like somewhere. Okay, so this is the condition, and under this condition, then this initial data set has the metric GT and the second fundamental form KT, for which I just wrote down a formula in components. Okay. So as a mathematician, yeah, please.
Oh, I did. Someone did ask a question. The question was, why aren't we simply using the pullback of the original metric as the induced metric?
The pullback of the original spatial metric or the original space-time metric?
I think they meant the original space-time metric. This to make sense.
So this is a good question. So this is really the same thing as taking ds squared and restricting it to gmt plus gmt. Okay, this is another way to compute it. I could have taken the space-time metric and computed its restriction to the tangent space of this hypersurface, and I would get the same result.
Good. Okay, thanks. Yeah, I think that makes sense. Thanks.
Sure. Okay, so whenever someone throws such a formula at you, make some sanity checks. So let's make some sanity checks. So the sanity checks is that both GT in components and KT in components are symmetric. I told you the second fundamental form is symmetric, and you know that metrics should be symmetric. So let's look at the formulas. So here the formula for the metric is completely, the right-hand side is of course symmetric in IJ because G is, and the TI/TJ is also symmetric. And now for this longer formula here, it's also symmetric. The first two terms on the right-hand side here, they are the same with I and J interchanged. This is the Hessian of G with respect to the spatial metric G on the canonical slice. So this is also symmetric in I and J. And here we have TI/TJ that's clearly also symmetric in interchanging I and J. So this sanity check is survived. And another sanity check you might want to make is that if you choose the graphical function to not change anything at all, to be the graph of the zero function, or of any constant for that matter, then we're back at the canonical initial data set, and we get GT equals 0 by J is GIJ. Let's go here. This is the formula minus n squared TI/TJ, but T is 0, so its derivative by 0, so nothing changes there. And also the K equals 0 by J, if we look here, this vanishes, so the first term vanishes, this vanishes, so the second term vanishes. Here we even have the Hessian of the function 0, which also vanishes. And here we have derivatives of 0, so everything vanishes in the numerator. Data is also trivially well defined. That's the thing in the green bracket is ensuring that anyway. And then so we're back at the canonical initial data set. Okay, so what have I done now? Now I told you that every initial data set in the Schwarzschild spacetime, or actually in Minkowski, if we set m equals 0 in this mass m equals 0 in this computation, can be written as a graphical initial data set. Now showed you formulas for the induced metric and second fundamental form, and also of course for energy and momentum densities of this graphical initial data set. And it's a graphical initial data set, it provided that this green circled condition is satisfied. Okay, so let's look at the special case of Minkowski. M equals 0, and then this means that n of r is just 1 for all r. And then if we go back to these formulas, I'll just copy the formulas and then we will see what happens. Oops. So now if n is 1, if n is 1, this will just be Bij minus Bij. Nothing that informs us very much about anything. But if n is 1, this term will vanish and this term will vanish. And so will this term, because it takes derivatives of n. And what we will remain with is the Hessian of t with respect to the metric g divided by the square root 1 minus g squared. But then let's remember, if we're Minkowski, the canonical initial data set is such that the metric is actually the Euclidean metric delta. So I get the Kronecker delta Ij minus the Ij here, and up here I'll just get the usual Euclidean Hessian Ij of t divided by 1 minus dt delta squared. And this is a formula that's well known in Riemannian geometry and Euclidean geometry, actually, because you could do the same thing with Euclidean space as the ambient space instead of Minkowski as the ambient space time. So maybe some of you have seen this formula. So the second fundamental form in this Minkowski case, in the graph case, is in some sense just the Hessian with the scaling factor in the denominator. And Harry already asked me this. This works in any standard static space-time. Okay. Any questions? Not at the moment. So then let's move on and let's leave these graphical hypersurfaces behind us until tomorrow, I believe. And let's make some important remarks about second fundamental forms. For extrinsic curvature. So I defined the second fundamental form for a space-like hypersurface, so a hypersurface with time-like normal vector field in a Lorentzian spacetime. But you can also define the second fundamental form of any hypersurface in any Riemannian or actually semi-Riemannian manifold. And even with codimension 2, so let me write some or higher codimension. So I can define the second fundamental form for hypersurface Riemannian manifold with the same formula for its definition. So again, the rate of change of the normal vector in tangential directions. And then usually a little little h.
Hey, Carla,
Yes.
a question did come up just when you asked. I guess there's always a little delay. I think this is a good one. The question was, can the extrinsic curvature even in Minkowski space-time be zero or be non-zero, actually, I should say.
Yes, so the extrinsic in Minkowski space-time, a generic initial data set will be non-zero and will be given exactly by this formula here, right? So if T is non-constant and not affine, so that its Hessian is non-vanishing, then its extrinsic curvature, the extrinsic curvature of the slice will be non-vanishing. Remember the cylinder. Yeah, if I have the cylinder in Euclidean space, then despite the fact that Euclidean space is flat completely, and the paper being intrinsically flat completely as well, this has extrinsic curvature, which is non-zero, right? And for the same reason, some graphical hypersurface in Minkowski spacetime, which is not too tilted, so it stays space-like, right, will have extrinsic curvature. And this is the formula for the extrinsic curvature is one way to compute it is to write this initial data set as a graph over the floor, the t equals zero, little t equals zero canonical initial data set, and then it will arise as this Hessian divided by this scale factor. It's not really a scale factor, but they scale it, okay? So it's non-trivial. Okay, and this is because it looks curved, even though it's still paper. Okay? It's still intrinsically flat, but it looks curved, and that means it has extrinsic curvature. Okay. Any further questions? Okay, then let's go back to these remarks. So,
sorry, Carla. There was actually one other one. And the question was: are the coordinates on the slice, are they Gaussian coordinates?
No, actually, maybe I did confuse you in some sense. It doesn't matter which coordinates I'm choosing. All that matters is that whatever I'm choosing, whichever coordinates I'm choosing on the canonical initial data set as spatial coordinates, I have to choose the same ones restricted to the MT as spatial coordinates on the MT in order for these formulas to hold. Okay? Now that I computed these, I could in fact do the following. I could forget about coordinates again and write the induced metric is nothing else than the metric minus n squared dt tensor dt, and kt is nothing else than dt tensor dn plus dn tensor dt plus n Hessian of t, sorry, this is a nabla, minus n squared dn grad gt dt tensor dt divided by the square root. And then there's no reference to coordinates whatsoever. Oops. And I hope this makes it clear it does not depend on any choice of coordinates on the space, but of course I chose the time coordinate consistently with the time translation symmetry or with the Killing structure of the static space-time. Yeah, but for the spatial coordinates, there is absolutely no condition. But if I do want to do it abstractly, then I have to say what it means to have G now on the whole space-time, and I didn't quite say that. But if you're familiar with that, then there's no reference to coordinates whatsoever.
Thanks. And yeah, that was very clear, actually. And I just want to mention, I guess you have about 25 minutes. Sorry, because I keep on interrupting you with questions, but you have 25 minutes left, I guess, until.
I mean, I love the questions, and I love the fact that there are questions, and I'm not. I still have time until tomorrow to modify the plan for tomorrow so that I cover what I want to cover in enough detail to fill the time tomorrow. So feel free, no worries. Okay, so let me say this again. I defined you the second fundamental form for a space-like hypersurface in a space-time at the beginning of this lecture. And then I gestured with hypersurfaces in Euclidean space, pretending that I also gave you a definition there. I did not, but the same formula for the definition of the second fundamental form as variation, as the rate of change of the normal vector in tangential directions gives you the standard definition of the second fundamental form, aka extrinsic curvature, for a hypersurface in a Riemannian manifold. And then we don't use the letter capital K, but we usually use the letter little h in the math literature for that. But the ideas and the geometry and the intuition about it is exactly the same. And the same spiel as before. People do not consistently have an opinion about the sign of this object, so beware that other references may use other signs in of the second fundamental form. And also, if we're not in a space-time context, but in a Riemannian context and having, say, some hypersurface, some two-dimensional surface and some three-dimensional Riemannian space, as we will tomorrow, then there is not really such an easy notion of which normal to pick. I said in the space-time context, we always pick the future normal, but here, none of these normals is better than the other. So if the surface is closed, like this, somehow, then I will always use the outer normal, and I will denote this normal by nu. But if the surface is not closed, there's no preferred notion of normal. Yeah? And again, also there, people have different opinions about which normal is more relevant, the outward one with the inward one, and they will define the mean curvature, or, second fundamental form with respect to whichever normal they like. And all of this just amounts in a change in sign. And as long as you use one definition consistently, there's no problem. But you shouldn't mix references on this unless you're taking the signs into account properly. Okay, good. So if we're in the Riemannian context and looking at hypersurfaces, we also have a notion of normal and second fundamental form. And also in higher codimension, so if I have a two-dimensional surface in a space-time, that will happen tomorrow. One can also define a second fundamental form, and it will be vector valued into the normal bundle. Okay, so let me draw a picture.
Actually, Carla, just before you draw that, there was one question, which was, how does this formalism only apply to globally hyperbolic space-times? Would it work, say, if you had a closed space-time?
The question is, would it work? What is the it, right? I mean, the definition of the second fundamental form is completely local. So if you pick a point in your hypersurface, and then you pick a neighborhood in space-time of that hypersurface, and you pick the neighborhood suitably small that the closeness doesn't interfere, then you can, and you pick a choice of normal there, then everything can be done locally. But of course, you run into trouble if you want to do it globally and you don't have a canonical future-directed normal because it's closed. Yeah,
I see. So maybe the question was if it doesn't use asymptotic flatness or anything, this sort of general construction.
At the moment, all that I'm saying is make complete sense locally, and if you're in a globally hyperbolic space-time, it makes sense globally. But the considerations are completely local.
Okay, thanks. Yeah, I think that was what he was asking.
Yeah, thanks. Okay, so let me draw a sketch of the situation we will encounter also tomorrow. So if we have a space-time and now some initial data set, not necessarily a canonical one, I'm just drawing it flat so I have enough directions to draw on. And then inside this space-time, we have a two-dimensional surface inside this initial data set. So now we have the four-dimensional space-time that I called L, and the three-dimensional initial data set that I called M, and now we have in that initial data set a two-dimensional surface sigma 2, then we can forget about the initial data set and consider the sigma 2 as a codimension 2 surface in the space-time. And as such, it has a vector-valued second fundamental form, which I'm not going to draw, but what happens is that this vector-valued second fundamental form has values in the normal bundle, in the two-dimensional normal bundle to this surface in the space-time. Okay. I will draw something in there in a second, but let me write something before. So in all these scenarios, including the one we discussed in length, in all these scenarios, it is instructive to compute the trace of the second fundamental form with respect to the spatial metric, and this is called the mean curvature. So this would be an interesting average over this second fundamental form behavior. And this would be the inside. So the initial data set inside the space-time name, and in the case of a surface, I told you that a two-dimensional surface now inside the initial data set, so still codimension 1. This little h here is the letter for the second fundamental form of the sigma in the M, and this little sigma here is is the induced metric. That's the name we're going to use. So we have here mgk, here LDS squared, and on this we also have a Riemannian induced metric, and we call it sigma, and its second fundamental form is H. Now this is inside the initial data set. Okay. And then there's one more object that's going to be important tomorrow, and that is the mean curvature vector. In 4-dimension 2. And I'm going to use this symbol for it. And let me first draw into my sketch. So if I have some point here on this surface, 2-dimensional surface in my 3-dimensional initial data set in my 4-dimensional spacetime, then this point P is of course just a point in spacetime also. It's also a point in the initial data set. As a point in the initial data set, I know that it has a future time-like unit normal locally, yeah, which I called N. Then as a point on the surface in the initial data set, it also has a space-like unit normal nu inside the initial data set. So now these two N and nu span the normal bundle of the 2-dimensional surface at this point P. And then this mean curvature vector, H, yeah. H is some vector also in this normal bundle arising as the trace of the vector valued second fundamental form, to which I didn't give a name, and traced over the 2-dimensional surface. Okay? So with respect to this induced metric sigma, and this H will look something like this. So this is now a 4-dimensional vector, so a vector with the length of which I can measure with respect to the Lorentzian metric at this point P, telling me something on average about the extrinsic curvature of this 2-dimensional surface inside the space. And it's a pretty straightforward computation to show that this mean curvature vector can be decomposed as follows. Okay, so I'll explain the object here. H, yeah, is this H. So it's the mean curvature of the surface within the initial data set. Next, this nu is of course the space-like normal to the surface inside the initial data set. N, I told you, is the space-time normal to the initial data set at this point. And the remaining term, this trace sigma k, is now the trace of the k here, of the second fundamental form of the initial data set inside the space-time, but only traced the tangential part to the 2-dimensional surface being considered in this trace. Okay. So this is what this mean curvature vector is. And another thing we're going to use tomorrow is this scalar quantity, which then is the squared, the S squared of H. Okay, so this is the length. So this is what we call space-time mean curvature of sigma. And this is a squared. Yeah. This is a term that's going to be important tomorrow. Any questions? Okay, so just to give you some intuition, here's some intuition about these objects, despite me rolling cylinders and graphs. In the Riemannian case, so when the ambient space is Riemannian, for example, with Euclidean, then this mean curvature H of a hypersurface corresponds to the rate of change of area under normal variations. So if H is positive, then if I vary my surface a little bit in the ambient Riemannian space in normal direction, like this, for example, then varying it makes the area larger. H equals 0 is what people call a minimal surface. And you might have already encountered this when you look at this Riemannian Schwarzschild, so T equals 0 Schwarzschild. Then as you approach R equals 2m, then this has 0 mean curvature. Also in the codimension 2 case, if H is 0, or actually if it's null, then this 2 surface, of which the H is null inside the ambient spacetime, corresponds to a section of the black hole horizon. Of the A black hole horizon. And this is safe. Okay. But that's where this mean curvature, space-time mean curvature vector becomes important. So in other words, this is saying that this H is 0. And also the second fundamental form K of an initial data set inside a space-time corresponds in a Hamiltonian perspective to the vaguely, up to some modifications, to the infinitesimal momentum of the initial data set in the space-time. Okay. Now let me jump back to something I already mentioned. There's a fact, which is an important theorem due to Choquet-Bouhat, and another important theorem due to Yvonne Choquet-Bouhat together with Laroche. And also since then to many other authors in other gauges and other regularities and other meta models. And that is that somehow space-time can be reconstructed from initial data. Okay, and a meta model. For suitable meta models, of course. And this is, of course, up to isometry. So if I give you initial data, then you can construct a unique space-time, unique up to isometry, say in vacuum, generated by these initial data sets under the Einstein equations. And if I give you space-time, then you can, which is globally hyperbolic, and I can look at a time function and take or a Cauchy hypersurface and consider that Cauchy hypersurface with the correct data to be an initial data set. There's another fact that's going to be important tomorrow. This one is not going to be important tomorrow, which is why I'm being vague. And that is that if you take your Einstein equation, this is the Einstein equation, and you combine it with the so-called Gauss, Ragazzi, Mainardi equations for hypersurfaces. So these are facts relating the geometry of say a spacetime or some Riemannian manifold or semi-Riemannian manifold to the geometry, the intrinsic metric, and the second fundamental form of a hypersurface. If you combine those with the Einstein, then you get the so-called Einstein constraint equations. Which read that the scalar curvature of the metric G, induced metric G plus base G squared minus K G squared is 8 by 16 by d over t squared mu. That's the Hamiltonian constraint or energy constraint. And also the divergence with respect to g of k minus trace t squared g is minus 8 pi g to the 4j, where j was the momentum density. So for any initial data set where I'm given the manifold M, so this is on M, the metric G, the second fundamental form K, or metric 0, 2 tensor field K, some matter density mu and some matter density J, they are only allowed to consider in this context if these constraints are satisfied. You know, a similar phenomenon from electromagnetism where you can't just use any initial data, but your initial data have to be satisfying certain constraints. And this is the case here as well. And of course, this first fact about the construction of the space-time is only true provided the constraints are satisfied.
Okay, Carla, as soon as you finish this thought, I guess there were a couple of questions which came up, so I should deal with them. So the first one was, how are these quantities? And I assume the question is about your construction earlier, like your mean curvature vector, etc. How are these intuitively defined at the r equals 2m surface and the r equals 0 singularity? So is there a relation, you know, are these things well defined? Because the space-time metric would be have a problem there.
So no for r equals 0. They're not defined there. That's not a proper hypersurface or surface in any sense, not even in the Kruskal-Takacs extension. So I'm not going to go to r equals 0. This is all outside. I'm always assuming in my Schwarzschild approach, in this graphical approach, I maybe should have stressed this more. I'm always concerned only outside this 2m radius, right? I'm excising the ball. So r equals 0 is not there, but r equals 2m is, and the why I'm allowed to say that this r equals 2m surface t equals 0, so this is all at 0, right? Is because there is a coordinate chart called isotropic coordinates on t equals 0 Schwarzschild. Some people call this Riemannian Schwarzschild or spatial Schwarzschild. And in these isotropic coordinates, the r equals 2m surface is a perfectly regular two-dimensional hypersurface. Okay, and so I can write this Schwarzschild metric. I put a little index m for Schwarzschild of mass m, perfectly fine as this 4 times the Euclidean metric delta, where s is some new radial coordinate which is different than r, and then s equals m over 2 corresponds to r equals 2m, but this holds for s positive. So in this coordinate chart, this is not singular at all, and I'm not doing anything in the space-time here. I don't have to go to Kruskal-Takacs coordinates. This is just in the spatial slice, in the time slice in the initial.
Good. Now there's one other further question, which was, I think, quite pertinent, which was, is the horizon always a minimal surface? So does it always have h equals 0?
A black hole horizon?
Yes, I think that's what they're asking.
No. A horizon always has this, and we call that this vector here had this form. So then this can be rewritten as h squared minus this trace sigma k squared. So this is not the same as saying that the straight h, so the spatial mean curvature vanishes. But in the case where k is 0, this is called the time symmetric case, which we have for the canonical initial data set in the Schwarzschild spacetime or the Minkowski spacetime or any other standard static spacetime, then it's the same as a minimal surface. Okay, so if K is 0, then minimal surfaces and horizons related, there's some stability conditions that one should impose. So this is just a necessary and not a sufficient definition of a horizon for sure. But all horizons have this curly H equals 0, all cross sections. And again, I'm being vague. Maybe I should say almost all, because there are some subtleties, but minimal surfaces are only correspond to black hole horizons in the time symmetric case or in situations where, for other reasons, this happens to vanish.
Good. And there was one final one, sort of came together. And that was, I'm just trying to paraphrase it slightly. Essentially, the question was, does one need this technology to go from 4 to 3 to 2 dimensions? Or like, why is that relevant? And the question was, I'm sure this will be explained tomorrow, but couldn't you do this from the space-time perspective?
Yes. So if I was only interested in the curly H vector or the curly H scalar, I could do this entirely without the reference to the initial data set. And that's a great observation. In that case, there are reasons that I'll explain tomorrow why I am imagining myself sitting inside an initial data set. And in a nutshell, it's because I want to say what is the total center of mass of that initial data set with the help of two surfaces. So the two surfaces automatically sit inside a given initial data set. Okay, so there's a strategic reason why I want it. And also I wanted you to see this formula here. Yeah, that you can actually compute this mean curvature vector from information within the slice, the first term, and information normal to the slice, the second term. So indeed, to define the curly H properly, I wouldn't need the initial data set whatsoever.
Okay, no, that's really good. Now, okay, so I have to warn you, I guess technically you have 1 minute left, but I don't mind if you go, a few minutes extra to finish your, finish your train of thought.
Okay. So I'll try to be as brief as possible. So the take-home message of I want you to carry on for tomorrow and maybe to digest is that initial data sets are the central object when you study the Einstein equations as an evolution problem, if you're not so much interested in the evolution. And they always have to satisfy these constraint equations, and you now understand all the terms M, G, K, mu, and J coming up when looking at initial data sets. And we also understand geometrically, hopefully, well, what the K means, and also what mean curvature and second fundamental form are for two surfaces inside initial data sets and inside spacetimes. And one last thing I wanted to say, if you look at the constraint equations as a mathematician, and you will see this a lot in math papers, mathematicians like to not say what mu and j are, and just understand mu and j to be defined through these constraint equations, okay? So they will tell you an initial data set is mgk, and mu and j are just things defined through these equations, and we don't have to think about them anymore, okay? So if that occurs tomorrow accidentally, then I apologize in advance, but it's a legitimate and helpful perspective to some of the things in mathematical relativity. Thanks.
Okay, perfect. You ended exactly on time. So I guess I'll allow for a few more questions. And in the meantime, maybe I can just ask a quick one. I guess technically we're out of time. I'm sure Ivan won't mind if we go 4 or 5 minutes extra in case people had other questions. So in response to a question just a minute ago, you mentioned there was a square of this mean curvature vector, and you said, and you created a scalar and you showed when there's a horizon, this thing has to be 0. I think you wrote it just a bit above. And you mentioned so when the extrinsic curvature is 0 in the space-time, then it's just a minimal surface. So I wondered if that formula, that h squared, is that related to what people often refer to as
the outward null expansion. So if you have a margin on
Yeah,
your
right.
surface.
Yeah, that's a good question. So maybe let me write this somewhere else. So what you find is that depending on your conventions, this h squared is
Yes.
theta plus times theta minus.
Okay, yeah, that's great.
Okay. So that's why I'm saying it's necessary to vanish if you are on a MOTS, on a black hole horizon section, but it's not sufficient because you can't tell which one would vanish.
I see. Okay, I
Okay.
see.
That's one of the subtleties I've swept under the rug, and I'm not going to talk about horizons anymore tomorrow. I just wanted to make the connection of the object, and so yeah, thanks for that question. So that's what's happening.
I see. No, thank
so
you.
you could rederive all of this in terms of the null geometry. Instead of using n and nu to span the normal bundle, you could use L plus and L minus, the light-like normal directions, and then you would see that.
Okay, that's really good, because I think a lot of people, at least here, we use that null formalism. So I'm really happy I saw that connection, because one side was quadratic, so I knew it couldn't be theta, but now you show me it's a product of the two, which makes a lot of sense.
That's one of the reasons why I prefer to work with h squared rather than h. But so it's also in some sense a theta squared.
Now I'm still waiting for any more questions. So guys, please go ahead. And in the meantime, Carla, if there's anything else. Oh no, there's one right here. This question was, could you share the derivations of the constructions that you derived? Now, I think you mentioned there was a paper that where you explained this in detail.
Question. So it's on archive. Okay, so it's also my only paper with Christopher Nertz. I'll pull up the references here again. Let's see. Yeah. So these are the references. This is NERZ is the co-author, and the paper is on archive. I'm not sure if I'm allowed to share the published version. But feel free to shoot me an email if you can't find it. So.
Okay. Let's see. Okay, well, that answers that. So maybe I'll just wait another minute or so, because I guess we're eating into the break here, but so there's always lots of questions, and don't mind waiting. Okay. Of course, people can always ask you stuff tomorrow as well.
Yeah, of course.
That's good, and I certainly don't want to keep your time. Oh no, there's Simple comment was simply great talk, which I would also echo as well, because that was very informative to me, and it shows you can learn. If you think you know something, you can always learn stuff from an expert in any area.
Yeah, I feel the same.
You can never read about this stuff in a book, so this is our chance to ask questions, and then you understand the jargon of things. Now, someone did ask you to have a copy of your notes, so that's certainly up to Carla. If she would like to share her notes,
I'll be happy to share them. I mean, I don't know how good they are, but because I always scribbled again on things for the app, but I'll be happy to share them. I can send them to Hari maybe tomorrow, or maybe even now if you want to have them before tomorrow. Yeah, I can send them to Hari right away.
Okay, yeah, by the end of the day, or whenever you have time, and then maybe just so people can see the PDF.
Or is there a chance to post them in the Slack? I have never posted a document in the Slack chat.
Yeah, you could post them in the Slack. You could just drag and drop into the Slack, and that should work, I think.
Oh, I have Slack on my phone and the notes on my tablet. Okay. I'll email them to you, and but you should feel free to post them in the Slack.
Okay.
Okay, no, thank you. Yeah, that'll be good. All right, so maybe just for the sake of being sort of on time, so it's 7 minutes ahead, maybe we should stop things down. Thank Carla again. Thank you, and I guess we will start again at
Okay, maybe Ivan, you can tell me. That's in one.
In about an hour, a little bit less than an hour, because I know a bunch of people have been confused on the time. So in an hour, well, at 12:30 Newfoundland time, which is 53 minutes from now, we'll restart. But I'm going to go eat my lunch now, but I'll be back in like 25 minutes for if Daniel, I know, is speaking next and he may want to check his slides. But anytime after
Great.
that.
Great.
Thanks.
Okay, guys. So we'll leave link open, and thank you very much again, Carla. That was really awesome, and looking forward to your talk tomorrow.
Thanks.
Thank you.
See you tomorrow.
Yeah.
Okay.